Okay, so let me talk a little bit about probability. That last question was asking us to predict the probability of having a certain genotype in offspring, in a group of offspring. So probability is used a lot in genetics, and it can be kind of confusing. And one of the questions I went over today in lecture was this question right here. So if I were to toss a penny and a nickel, and each coin has a 50% chance, 0.5 probability of being heads, what is the probability that one will be heads and one will be tails? So one of the coins will be heads and one will be tails. So probability, one coin is heads and one coin is tails. Now, the natural tendency here is to just multiply, 50% chance of the coin being heads and then 50% chance of the coin being tails, and then getting 1/4, which would be wrong because of the way the question is worded. So let me diagram this out. So there are 4 possible outcomes of events, let's say, concerning the penny and the nickel. So if we flip the penny and the nickel, so first time we flip the penny, maybe it comes up heads. And then we flip the nickels, and maybe that nickel and it comes up heads. Okay. So there's a 1/2 chance of the penny being heads, and there's 1/2 chance of the nickel being heads. So we can say there's a 1/4 chance of both the penny and the nickel being heads. So there's also a possibility, if we flip these 2 coins, that the penny will be tails and the nickel will be heads. So there's a 1/2 chance the penny will be tails and a 1/2 chance the nickel will be heads. We can multiply these together. And okay, overall there's a 25% chance that we will get this outcome with the penny tails and the nickel heads. However, maybe the penny is heads and the nickel is tails. So that's a possibility too. We haven't recorded that possibility, but it's definitely possible. You can multiply that together. There's a 0.25 probability that this outcome will occur, this combination of events. There's one more combination of events that is possible, both of them being tails. Again, so you flip a penny, there's a 50% chance it's going to be tails. Flip a nickel, there's a 50% chance it's going to be tails. Together, multiply those together, you get a 1/4 to 0.25 probability, 25% chance that the outcome is going to be both tails. We can add these up, and we've accounted for 1.0 or 100% of the outcomes. So we've accounted for everything that is possible if we were to flip these 2 coins, assuming the coin's not going to land on its side. So the question asked us, what is the probability of one of the coins being heads, one of the coins being tails? And you can see there are 2 ways, right? 2 ways to get the situation or the outcome where one coin is heads and one coin is tails. And the second one right here, so combination 2, penny is tails, nickel is heads. Combination 3, penny is heads, nickel is tails. Okay, so we need to add these together. 1/4 plus 1/4 equals 1/2. So probability of 0.5 or 50% chance that if we flip these 2 coins, one will be heads and one will be tails. Now, if we were to specify what is the probability that the penny is tails and the nickel is heads, Well, this is the only combination of events that satisfies that condition. Penny tails, nickel heads. And then we could say, oh yeah, okay, that's only a probability of 0.25, 25% chance of occurring. Now this is important for genetics because we're often interested in combinations of events to a certain outcome. And let me give you an example here. So a couple plans to have 2 children. What is the probability that they will have 1 boy and 1 girl? This is just like the coin problem we went over, and we're assuming here that for every fertilization event, there's a 50% chance that that fertilization event is going to create a boy, and a 50% chance it's going to create a girl. So there are a number of ways to get 1 boy and 1 girl if a couple has 2 children. So let's say child 1 here, child 2 here. We're assuming no twins here. So combination 1, let's call these combinations, combos. So combination 1, 2 boys. The couple has 2 boys. Okay, that doesn't satisfy our condition. Combination 2 is possible. Boy is born first, girl is born second. Combination 3, girl is born first, boy is born second. There's still one combination we haven't accounted for. It's possible 2 girls will be born. Now, just like the coin problem, each of these has a 50% chance of happening. You have to multiply those together to get the probability of this combination of events occurring. So probability of 0.25, 25% chance of occurring. Each of these is the same. So add this up, we get 1.0. We've accounted for all possible combinations of boy and girl that could possibly occur if these parents have 2 children. But the question is interested in these right here. So the probability that they will have 1 boy and 1 girl. We didn't specify having a boy first and a girl second, or a girl first and boy second. We just want to know the probability of 1 boy and 1 girl. So we have to add those together, and we get 1/2. So a probability of 0.5, or 50% chance that if a couple has 2 children, 1 will be a boy and 1 will be a girl. Only a 25% chance they will both be boys, and a 25% chance they will both be girls. Now, these questions can get more complicated. We can do these ones right here with just 2 kids or 3 kids by hand, as long as we are careful and we account for all the possible ways, all the possible combinations of events. It gets harder when we get up to 4 children. So what is the probability that this couple with 4 children will have 2 boys and 2 girls? Well, we could start by hand, right? We could start this problem working out by hand the probability here. So we'd have to keep track of all the outcomes. And I just would like to start with the 4 different events. Each event is a childbirth. The case where we have 4 boys. Okay, so if they were to have 4 boys, what is the probability? It's going to be 1/2 by 1/2 by 1/2 by 1/2. 1 out of 16. So if parents have 4 kids, there's a 1 out of 16 chance that they will have 4 boys. That's the only way they can have 4 boys, is to have a boy each time. So we don't have to worry about any other combination of events there. 3 boys and 1 girl. So if we had to figure this out by hand, we could just, assume a girl is born first, and then 3 boys. Maybe the girl is born second. Maybe the girl is born third. Maybe the girl is born fourth. Now each of these is going to have a 1 out of 16th chance of happening. So if we are just interested in the overall probability of the couple having 3 boys and 1 girl, we would need to add all of these together. That would give us 4 out of 16, or 1/4. So there's a 0.25 probability that they will have 3 boys and 1 girl, 25% chance. We could keep going, and you would see this is the same thing for 3 girls and 1 boy. And if you wanted, you could do that just by changing all the G's to B's and B's to G's. And you see it's the same thing for 3 girls and 1 boy. There's a 1/4 probability, 0.25 probability, 25% chance. Also, same thing up here. For boys, there's a 1 out of 16 chance of having 4 boys. There's also a 1 out of 16 chance of having 4 girls. But what about 2 boys and 2 girls? So here's the table. I'll print it out where we can see all boys, 3 boys, 1 girl, 2 boys, 2 girls, 1 boy, 3 girls, all girls. Now you can see there are 6 combinations here that can lead to 2 boys and 2 girls. You can pause the video if you want and take a look at the diagram. This is also in the notes. So we could just add these up now. 1, 2, 3, 4, 5, 6. And there's a 6 out of 16. There's 6 out of 16. How's the way to say this? I don't know how. 6/16 probability, I should say. Sorry, 6/16 probability, or 3/8 probability that the couple will have 2 boys and 2 girls. So that's pretty neat. Of course, on an exam, you might not be able to, or a quiz, you might not be able to complete this table fast enough to get the right answer. So I'm going to give you a shortcut method, and the shortcut is called the binomial shortcut. And this is the binomial shortcut. It looks pretty scary, but it's actually really easy to use. So P is probability, N factorial. N is the total number of events, so the number of kids in this question. S is the total number of events of type A. In this case, we can call it boys, number of boys born. T, number of events of type B. In this case, we can call it the number of girls born. And we're going to multiply that by A, number of boys. Actually, no, A is the probability of having a boy, raised to the number of boys. And B, probability of event B, raised to the number of events of type B, in this case, girls. So let's plug that in. Well, I'll show you how to solve this. So let's solve this for the question where couple has 4 kids. Probability, what is the probability that 2 are boys, 2 are girls? Now, let me plug this in. N, like I said, number of kids. S, number of boys. T, number of girls. A, probability of a boy at each event, 1/2, right? Raised to S, the number of boys. And B, probability of a girl, raised to T, the number of girls. Now we have to solve this. Factorials are easy. We just need to expand them. So 4 factorial means 4 times 3 times 2 times 1. 2 factorial is 2 times 1. So this is also 2 times 1. Now that's the expanded part of this, of the formula is right here. So we can solve that by crossing those out because they're on the denominator and numerator. And then we have 12 over 2, right? So that equals 6. So we need to multiply 6 by, we need to multiply this whatever this works out to by 6. So 6 times 1/2 squared times 1/2 squared equals 6 over 16 equals 3/8. So this is what we worked out before, right? Do I have that sheet somewhere? Ah, okay. So probability of a couple who has 4 kids, having 2 boys and 2 girls, we said is 3/8 according to this formula here. And that's what we calculated over here. So this is a handy equation, and you will get this on the exam or quiz. You will get a copy of this equation, but you'll need to know how to use it. Now, in class, we went over a twist. Let me see if I can find the question here. No, I think it was in our group activity. Okay, so in a family of 4 children where both parents are heterozygous for albinism, what is the probability that 2 will be normal and 2 will have albinism? So this is a little different than the boy and girl question, right? Because there's a 50% chance of having a boy or 50% chance of having a girl. If you have 2 parents that are heterozygous for albinism, now the probability of them having 1 child with albinism is not 50%. There's not a 50% chance. And we can see that with the Punnett square. All right, we're going back to lecture 3 here with the Punnett square. And we can see these are the gametes from the parents. And there's a 3/4 chance of having a child that is normal, and a 1 out of 4 chance of having a child with albinism. Okay, so these are the individual probabilities for each child that's born of being normal or having albinism. So we have to use these probabilities, not 1/2, in the binomial shortcut formula. So again, the formula is P equals N factorial, S factorial, T factorial, A raised to the S, and B raised to the T. N, number of kids, 4. 2 normal, 2 albinism, probability of normal is 3/4. We want 2 kids normal. Probability of albinism is 1/4. Raise that to 2, because the question is asking us for, 2 normal, 2 having albinism. So we need to expand this. Sorry, this is 4 factorial. So we worked out before in the last problem, but you know what? I'll do this. I'll do it out. 2 times 1 times 2 times 1. We got 12 over 2, so that's 6. So this, we solve this. The answer is 6. We have to multiply this. We're going to have 9 over 16 times 1 over 16, which works out to, this was 256. I believe we did this in class. 6 times 9 is 54, equals 27 over 128. Okay, now that's the answer to this guy right here. So little twist in here, right? When we're talking about boys and girls, the probability is 1/2 for a boy, 1/2 for a girl. When we're talking about albinism, 3/4 normal, 1/4 albino, and there could be a different probability on the quiz or the test, but I just want you to keep in mind you just can't plug in 1/2 into A and B and expect to get the right answer. So think of the question, think of what the probabilities of inheriting one condition over the other, or being a boy or a girl, before you just plug those probabilities in there.